So I just wanted to give you a little bit more updates on what I've been doing slowly, trying to improve the Brewer Umkehr retrieval algorithm. As you probably heard, there are several outstanding issues trying to characterize the polarization of light in a brewer. It's one of those, and I haven't figured out how to do it yet, so kind of interested to learn from Henry. This is Aloha Station, if you haven't been there. And you can see there are several brewer instruments there. And somebody put this sticker of NOAA on one of the brewers that belongs to Environment Canada. But we also have Dobson instrument that sits next to the brewers. So they take measurements pretty much. Well, they're not synchronized, but I mean, you get a lot of overlapping measurements. Another instrument that sometimes comes into configuration is the ozone sounds. They are not launched from Mauna Loa. Mauna Loa is a high altitude station, so you have to go down to the sea level. It's HELO, and they launch balloons once a week. So we often use the ozone sounds to try to verify our measurements. There is yet another instrument that sits in there, which is not showing up here. It's a microwave, so you get the microwave profile. You actually have also LiDAR profile and FTIR instrument. So you have, it's a super station. It's a wonderful station with many, many kind of measurements. I think I already mentioned that although the two instruments are not created equally, that you have some similarities, some differences between the Dobson and the Brewer. They're both measuring Umkehr, meaning that they're looking in the zenith sky when the sun is going up and down, whereas Dobson has the wavelengths that are not really individual channels, but they're rather the ratio between the two channels. With Brewer, you have an opportunity just to record zenith sky measurements at the different wavelengths. But there is some price you have to pay using Brewer measurement, is that the measurement is polarized. So in Dobson it's not polarized, and in Brewer it's polarized, which creates a little bit of a problem for me, because I haven't been able to totally reproduce the Brewer Umkehr measurements so far. So that becomes a challenge. Then there is also an issue for the Mark IV, which is located in Boulder, that part of the NEU Brewer, no EPA Brewer network. That is Mark IV, and it has a nickel sulfide filter, which you also have to figure out how to implement in your retrieval techniques. And it's aging with time. And sometimes the agent is not linearly propagates through the old wavelengths, so you have to be careful about that. So that there are simulated profile retrievals that are produced by both Dobson and Brewer. And we have several records. In Boulder, the record began in the fall of 2006. But in Mauna Loa, some of the Environment Canada records been known to exist since 1998. And there also has Brewer measurements since 1994, which I hope at some point to start looking at. So you have a choice of doing different ways, different algorithm to derive Umkehr ozone profile. The one algorithm that is developed for the Dobson, and it's a modification from Carl Metier, old 1992 Kirka algorithm. And I'm saying that Tom McElroy is working on be able to read from the B files and produce ozone data sets 6 months from now ongoing, right? Okay, so here we go. There is another version that I'm trying to develop, which would be using several spectral channels, which would be beneficial, I think, for many people to use, since that doesn't require you to to wait until the sun rises up to 70 degrees Celsius angle. So it will be more fitting into the schedule of the operating of the brewer. And it requires some preprocessing the software. So I'm going to work with Martin, trying to put it in the same package as he has for the currently for a PC version of the brewer retrieval for using single wavelength pair. So this is the measurement of Brewer 141 in Boulder. You have several wavelengths where you measuring Umkehrs during the day. And then the C pair is formed by these two wavelengths, which is 310 and 326 nanometers. But you can use all of these wavelengths, and then you can stick with the measurements that are just within that range of the Celsius angles. I already showed that, but I wanted again to emphasize that between the single Brewer and Dobson retrieval, you get pretty much similar information content by looking at them, averaging kernels together with the error analysis. You get a little bit better off by using multiple spectrum retrieval. So this one is a demonstration of various things I was trying to do, trying to improve the algorithm. And you can start by trying to choose the ozone cross-section. This is mass and power cross-sections. I did some tests using the different cross-section. This is Dumas cross-sections, and I also work with the new Bremen's cross-sections to look at how much of the effect you get. But here you have various things. You have the stray light in Brewer that you're trying to correct, which changes profile somewhat. Then you have temperature corrections that give you some sensitivity if you don't put the correct temperature in your cross-sections. You have, by the way, this one is the reference. Basically, I'm plotting everything against the standard Umkehr profile retrieval. But this is, you have the difference from what's been observed. And observed means that I have this profile and I can calculate what my Umkehr measurements should be. And I'm not really getting it with the standard profile, but I can tweak, do some stray light corrections and other things that I start to move closer to the what I want to get. It's my reality check. And so there are differences between different Brewer instruments, of course, that if you don't take into account their individual stray light characterization, that you will get slightly different profiles. And the same story goes for the Dobson. Dobson also has stray light issue. One thing that you have to face when you work with individual wavelengths is that you need the ETCs. And they are not really sometimes easy to get by. The 5 short wavelengths, and you don't really sometimes get even the 5 short wavelengths that I use for the total ozone. You get one constant. So there are some ways trying to avoid actually doing the Langley plots for your measurements. If you can do that, wonderful, it's much better. But it's extremely difficult, as we all heard today. There are various issues. So sometimes you can do just soft calibration, meaning that you try to simulate your measurements and then you compare it to what your instrument is measuring for day, and you plot it as a function of total ozone, and then you try to figure out what your offsets are, and so you put it into your algorithm and try to use it to correct for the instrumental constants that exist in your instrument, which you don't know sometimes. And so by doing all of these wonderful things, you can try to simulate those offsets. And in this case, Patrick did characterization of one of the instruments, and so we had the ATCs for different spectral channels. And here I'm just showing that this is his measurement, and I'm trying to reproduce them. And I can do it if I have a good idea of what my nickel sulfide spectral transmission is, and if I know what the stray light of the instrument is, I can do it. Otherwise, it's not very repeatable. And this is the point, I guess, the fact that I've discovered that if I use some kind of standard transmission function for the nickel sulfide, which is represented by this curve, but once Patrick measured some of the filters in the lab, you start to see there are some spectral differences. This is, thank you to Volodya. He gave me a bunch of measurements of the slit functions from the different instruments. So I picked specifically the ones that would be Mark IV. I don't know which instruments they are, so don't worry. I don't know all these secrets. So I have just the number 1, 11, 15, 16, 18. And I'm comparing it with something that is generic, typical strelite function that I was trying to use in the past. And you can see that I just have the typical distribution here with the dropping down to a certain level. Whereas the band passes actually tell me that there is more variability in the wings. So if I do simulations by using all these different functions and compare it to the standard typical band pass, that I could see that there are some variability, and especially it starts to show up at closer to the horizon. This is 310 nanometers, this is 326. This light blue one is the typical standard, and the other instruments are kind of scattered around that. So then I create my C pair, and I can try to look how much of the effect I'm going to get in the retrieved ozone profile if I don't use specifically instrument-specific slit function. And so this is my kind of rough estimate, so I can get about 5 to 5% in a stratosphere, plus minus 5% in a stratosphere difference, and I get about 5% difference in the troposphere. This one was, I decided to look what's going to happen if I use the different ozone cross-section. So actually, I don't know, I mean, I need to check this one, but with using the new Bremen cross-sections, I actually get larger sensitivity to the slit functions, and I'm not quite sure why that is specifically, but I will continue to investigate. So this is an example of using NASA Goddard instrument, and they did some measurements using typical Brewer routine, a couple of years, for 2 years. And so you can see here that you have the retrieval here, the data by using a single wavelength pair. The black one is a single pair, and then you get multiple wavelengths. This is red one. You can plot it also together with the climatology and or MLS data, so you can see how you capturing the variability in one of the layers. So you have still to deal with the data screening. And so we use the ratio of the two sequential measurements at 320 nanometers to detect the clouds in a view of the instrument. So we need to figure out the zenith sky light characterization for the zenith sky, stray light characterization, so that generic function is good, but it's probably not as good as you want it to be. And then still there is a hope to do more intercomparisons between the different instruments and the different stations. So this one is an example from Mauna Loa. The purple one I mentioned is microwave, right? So you have microwave measurements, and then you have the black one is here. I think it's no, I don't remember. Oh, it's a Dobson, and then you have green one, which is a Brewer measurement, and you can just plot it as a ratio versus the climatology, and you can see variability, and there are some differences here that we observe against the microwave. This is just plotting the Mauna Loa Dobson data from the Umkehr measurements, plotting the Brewer measurements. At Mauna Loa, there are some differences between the Dobson and the Brewer. There are some issues here. Sometimes the screen for the data does not work as well as you want to. You have integrated ozone sound data for 2004 to 2006 at Mauna Loa. You can apply the averaging kernels. It looks much nicer. See these broad features? Those are once a week measurements. You can do different statistical analysis, trying to compare data and look at how your distributions look like. You can do some references using the model because the sampling sometimes is an issue, trying to get enough sampling examples. You can do it against the models and just to look for the typical features. This is what we did back in Beijing. I want to skip the conclusion just to give you another glimpse of Boulder data. Sound, averaging kernel applied to the sounds. You have Dobson, you have Brewer, singles, multiple. So they all almost look the same, but they're not exactly the same. And that's what I'm trying to do. I'm trying to characterize the Brewer the best I can so that they will look exactly the same. So we're measuring the same atmosphere, the same ozone variability. So with that, I'm just going to leave you with these examples. So thank you.